Okay, so this is a solution to the set of problems really that we did about banked curves. And a banked curve is one where the person is going around, say, in a circular track, right? So they're going around in a circular track, but the roadbed is angled by some theta. And let's use r for the radius of the circle. And so this was a question about safe speeds, about what speed you can travel. And so let's do first the problem without friction. So without friction, you can actually go around in this circle. Without friction, you have some normal force away from the roadbed and some gravitational force mg. And to go around in a circle, where I'm drawing the free body diagram for the position of the little box or car or whatever it is, that's shown in the picture, so on the left-hand side, the acceleration is always inward. And if we choose axes x and y, the normal force is separated into components, and the sum of the forces in the x direction is Fn sine theta, and the sum of the forces in the y direction is Fn cosine theta minus mg. Now in the y direction, you're not going to slide up or down the road, so the acceleration is 0, and the x direction is that centripetal acceleration, v squared over r. Okay, so we don't know what the normal force is, but if we're trying to find the speed, let's go ahead and start with this top equation, and we get that Fn sine theta is mv squared over r. The bottom equation allows us to solve for the normal force and then substitute in, which I'll do sort of in my head here. The normal force is mg divided by cosine theta times sine theta is mv squared over r. The m's cancel, and that's key, right? Speed limit signs don't have the mass of the vehicle on them on purpose because the mass cancels, and we're left with g times sine over cosine is tangent theta times r. If I take the square root of that, I get the safe speed. So that's the answer, and what this means is that there's really only one safe speed to go around in a curve without friction. And so with friction, there's actually a range of speeds, which is good. I think that's something that we want here. So with friction, and it's static friction that is going to help us get around the curve at different speeds. Now, let's start with finding a maximum speed to go around the curve. If we're going to find a maximum speed means friction acts down the slope. So for friction acting down the slope, we'll do our same free body diagram that we did above. Let's see the normal force. Let's move it over here. The normal force went away from the roadbed, and now friction goes down the slope to keep you from sliding outward, and mg is downward, and still we have this centripetal acceleration inward. Okay, so we'll do the same thing we did before, x and y. The sum of the forces in the x direction is once again Fn sine theta, but now it's also the component of friction, where this angle here is theta. And the component of friction is friction times cosine theta, which is mv squared over r, and the sum of the forces in the y direction is once again Fn cosine theta, now minus the force of friction sine theta minus mg is 0. Okay, so we're going to do the same thing we did before, right? The same thing that we did before. And let's use this bottom equation. The normal force is, oh, wait a minute. The normal force appears in friction too. So at the maximum force you can get from friction, the force of friction is mu times the normal force. So let's rewrite both of these equations. Let's rewrite them. And in fact, I think what I'm going to do is I'm just going to rewrite them. So the force of friction is mu times the normal force. I'm just going to rewrite it in here inside what I've already done. So mu times the normal force, mu times the normal force. So now when I do my solving, I see that the normal force, I'm just going to rewrite this as cosine theta minus mu s sine theta is equal to mg. So the normal force is mg divided by cos theta minus mu s sine theta. And then I'll take that and plug it in the top equation. And I get that the normal force, mg cos theta minus mu s sine theta, that's the normal force where I've pulled it out as a constant factor. What's left is a sine theta plus mu s cosine theta is mv squared over r. I think we were using capital R there. There we go. Okay, so once again, the m's cancel, and we're left with that so notice up above, the speed was square root of r times g times tan theta. We're going to have a similar thing here, right? We're going to have that v is equal to a square root, and we're also going to have an r and a g, only now what we have is much more complicated. Sine theta plus mu s cosine theta divided by cosine theta minus mu s sine theta. So it's important to notice, I think, that where we had sine over cosine before, now we have sine plus something divided by cosine minus something. So we've added something to the numerator and subtracted something from the denominator. So this indeed is a bigger number. This is V max. This is indeed a bigger number. Now to do it with a minimum speed, well, V min, right, would just be swap the direction of friction. And you can do this in sort of a quick and dirty way by simply changing the sign of the arrow. So by making the arrow a negative number, right, that's the same thing as switching its direction. And this, which means every place we see a mu s, we're going to swap it out for a minus mu s. So you should do the problem from scratch, but you can show for yourself that V min then is equal to the square root of rg sine theta minus mu s cosine theta divided by cosine theta plus mu s sine theta. And if you want to simplify this, you can divide each side by cosine and get it into tangent and so on. But I think I'll leave it the way it is and go ahead and end there.